Let's talk about the shape of light. I like to begin by using a laser pointer because it's got a narrow beam distribution of light and a narrow spectrum. This is almost purely a green beam of light. For reference, this is some theatrical gel. I'm going to take this red gel and place it in front of the green laser, and you'll see almost no light comes through. There's not a shift in the color, there's just a reduction in the amount of light coming from that laser. If I use a less saturated red, you'll see a little bit more light coming through the laser. But again, no color shift because of how narrow the spectral distribution is. Let's actually look at some more theatrical films, but talk more about distribution of light and shaping the beam. So this laser, again, very narrow beam distribution, so we can really see when we add optical films how it changes the shape of the laser. I'm going to start with a frosted, a theatrical frost, essentially. And what we'll see here is that the laser beam spreads out a little bit. It softens towards the edges. Not a massive spread, that we still have some points. There's still the sense of a point. Let's use a medium level frost. So here's the laser and medium frost added. This really spreads that beam out. You can see a significant difference. It's more like a 30-degree beam angle. And then let's use a wide 60-degree beam angle. So the 60-degree beam angle really does significantly spread out that laser. Here's the 60, here is the 30, and here is the beam softener, which doesn't stretch it out very much. And then the fourth and final one to show you, this is a linear spread lens. This will bend the laser perpendicular to the lines that are on the filter. So right now my filter lines are running across the filter, left to right. This will bend my laser up and down. So we see a vertical line of light. I can rotate the filter and thereby rotate the angle at which I'm bending the light from the laser. So these films are theatrical films and sometimes used for actually filming as well, these filters, but all of them have architectural equivalents. And we're going to look at some architectural lenses in a bit. Let's also talk a bit about surface reflectance. I like to use the lasers to talk about the way that surfaces reflect light as well, since the laser is so focused. We're going to talk about Lambertian distribution, Lambertian bounce off of the walls. This is a matte finish wall, so it's painted with just a little bit of reflectance versus eggshell or semi-gloss or gloss. A glossy wall will tend to bounce more light and reflection directly off the surface. With this matte Lambertian surface, if I am hitting it with the laser, it doesn't matter which angle I'm hitting it with the laser, it's going to show the same shape of laser over here. The bounced light continues to be an even blob, whether I'm hitting it at a pretty oblique angle or at a fairly straight-on angle. And that's because this Lambertian surface is bouncing the light, irrespective of which angle the light reaches it. Contrast that with using a mirror. Mirrors give you specular reflections, so angle of incidence equals the angle of reflection. If I use the laser to bounce the light off the mirror now, I will get, I actually have to angle this a little bit more, I can get a sharp bounce to that angle, that where it's landing on this wall has a direct correlation with the angle at which it's reaching the mirror. So specular reflections from mirrors versus Lambertian reflections from a wall that's painted matte. So we've talked through the laser pointer opticals. Let's actually take a look at an architectural fixture. This is a PAR 38. In this case, this is an LED retrofit lamp. I'm using this in substitute of a traditional halogen PAR 38, where you'd have a filament in the middle, the reflectors and the lenses gathering that light and controlling the shape of the beam. So the LED PAR 38s feature many of the same qualities of beam control, but using LED, so our optical packages are different. This happens to have a high 3000 Kelvin 90 CRI, so the beam renders color in stark contrast with the laser that we saw earlier. This is a narrow beam distribution, 10-degree beam spread, so we see the circle of light on the wall. A beam spread, by the way, is defined as 50% of the center beam candle power. Center beam candle power is the hottest part of the light, the brightest part. So roughly here in this image. The beam in this case is where the light drops to 50% of that amount, roughly down here and up here. So kind of that spread would be your beam spread. In this case, this is a 10-degree beam, so 5 degrees to either side of center beam candle power. That gives you an overall beam spread of 10 degrees. We can also discuss field angle. Field angle is defined as 10% of the center beam candle power. So out here is where we have field angles. And you'll notice that there's some striations seen here, that this particular optic from this PAR LED lamp, it's not as clean at the edges as I might like. And this shows also in section. Here's the center beam candle power lined up along the seam. The beam spread kind of comes out to these sides, and the field angle is visible out here. But we can still see noticeable striations. I'm going to add some filters. This is a 17-degree filter. This PAR lamp happens to have snap-on lenses, so I'm going to pop this on. And what you'll see is not a major change in the beam spread, but you're going to see the edges of the beam cleaned up noticeably. So I'll do it here. We still have a pretty good punch. It's now 17 degrees instead of 10, but our field angle has cleaned up significantly. We no longer see those striations and edges along the beam. A typical architectural glass that we use for this is called solite. Some other people call it microprismatic lenses. So a solite or microprismatic lens is meant to soften the edges of the beam and the field angle without manipulating the beam spread too much. You're going to still maintain a lot of that punch towards the center. Let's contrast this with, this is a 36-degree floodlight optic. If I add this on, it's going to significantly widen the center of that beam. It's really spreading it out across the lens. And the field angle has also been changed drastically. So here's the beam angle and the field angle for our 10-degree beam. And snapping that optic on smooths this out. Now we have more of a 36-degree floodlight rather than a spotlight. We can go even wider. This is a 60-degree lens. This is going to take this, this punchy beam of light and turn it into a blob. So here we go. This is now our 60-degree beam of light. We don't use these for art lighting. They don't tend to highlight things the way that you can with a spotlight, but they can be very useful if you want general diffusing downlights, in corridors or other applications where you're trying to spread the light across a wide width. Because this is LED and not a halogen PAR lamp, we can also play around with some different optical technologies. This is a rectilinear spread lens, so we're actually going to get a square of light. I'm rotating that so you can see the square. It doesn't make a big difference if you're focusing it close to, in section you don't see much, but this can help imitate a framing projector. If you want to light up artwork or highlight a poster in a retail store, this is one way in which you can frame out that art. A more typical way to do that is with something called a framing projector or ellipsoidal projector. I'll be demonstrating one of those later. And then we also have a linear spread lens. This lens is going to, if I put the lens with the lenticular lines facing left to right, it's going to stretch my beam top to bottom. And you'll notice we still have a pretty good amount of punch, but now it's stretched more in this direction. If I rotate it, you can see it's now stretching this direction. These can be very effective for wall grazing, that if you're trying to maintain the punch of light up a wall, but spread it side to side, you can use a spread lens, and that will still punch the same amount of light up here, or nearly the same, but spread it out from side to side. The final optic I'll demonstrate is, this is a hexel louver, also known as a honeycomb louver. Let's take a look at how it optically changes the light. You should see very little change. Here's no hexel louver, here's the hexel louver. A hexel louver is intended to not change optically where the light is going. It's intended to improve the shielding angle or the cutoff of the luminaire. Each one of these prismatic fields is about 1/8 of an inch deep, and the honeycomb structure helps to provide better cutoff as somebody looks at the light from different angles. Very useful for art and retail. I'll demonstrate it here. I'm going to put a 60-degree floodlight on this and then put the hexel louver over it. And you'll notice as I tilt the light towards you, at a certain point it becomes very bright and uncomfortable. If I remove that hexel louver, the angle at which it's uncomfortable is much wider. That the 60-degree light, you can see the brightness of it pretty severely. By popping the hexel louver on, that's really improving our cutoff angle. So that if you imagine in a retail display, you're trying to light a mannequin, but people walking around it on the other side, you don't want to blind them. This is a very effective way to do that.